8, 7, 6, 4, 3, 2, 0, and liftoff for the final launch of Endeavour, expanding our knowledge, expanding our lives in space.
Houston, Endeavour, roll program. Roger, roll, Endeavour.
Houston is now controlling.
The Milky Way has been studied for centuries, its structure mapped through painstaking observations that progressed from naked eye counts of stars to sophisticated radio surveys and infrared imaging. Astronomers have constructed a detailed picture of our galaxy, a barred spiral approximately 100,000 light-years across, containing 200 to 400 billion stars, organized into a central bulge, a thin disk with prominent spiral arms, a thick disk of older stars, and a vast spherical halo of ancient stars and globular clusters. This architecture has been refined through decades of observation, with each generation of telescopes adding precision and detail. The model has been tested against observations of stellar motions, chemical compositions, and the distribution of gas and dust. It has survived these tests, becoming the accepted framework for understanding our cosmic home. What the James Webb Space Telescope revealed in its observations conducted between late 2023 and mid-2024 challenged aspects of this framework in ways that were not anticipated, suggesting that the Milky Way's history, structure, and current state were more complex than the standard model allowed. The basic structure of the Milky Way has been understood in broad outline since the early 20th century. Harlow Shapley's observations of globular clusters in the 1920s established that the Sun lies far from the galactic center, about 26,000 light-years out in the disk. Subsequent observations revealed the spiral arm structure, though mapping these arms from within the disk proved challenging due to dust obscuration. Radio observations of neutral hydrogen in the 1950s provided the first comprehensive maps of the spiral arms, showing that the Milky Way possessed a multi-armed spiral pattern similar to other disk galaxies. The discovery of the central bar in the 1990s, a rectangular structure of stars extending from the galactic center, refined the classification from a simple spiral to a barred spiral. Infrared observations, which penetrate dust, revealed that the bar is prominent and likely plays a crucial role in funneling gas toward the center, where it fuels star formation and feeds the central supermassive black hole, Sagittarius A. The bar's presence affects the dynamics of the entire inner galaxy, creating resonances that shape the spiral arms and influence stellar orbits. The galactic bulge, the dense concentration of stars at the center, has been characterized as primarily composed of old, metal-rich stars. Some models suggest it formed through the vertical heating and thickening of the inner disk, while others propose it resulted from mergers with smaller galaxies early in the Milky Way's history. The bulge is not spherical, but boxy or peanut-shaped when viewed from certain angles, a morphology consistent with bar-driven dynamics. The disk itself is divided into components. The thin disk, where the Sun resides, contains most of the galaxy's gas, dust, and young stars. It is the site of ongoing star formation and has a scale height, the thickness perpendicular to the plane, of only a few hundred light-years. The thick disk, composed of older stars with higher random motions, extends several thousand light-years above and below the plane. Its stars are chemically distinct, with lower metallicities on average, suggesting they formed earlier in the galaxy's history. Surrounding all of this is the stellar halo, a roughly spherical distribution of old, metal-poor stars and globular clusters extending hundreds of thousands of light-years from the galactic center. The halo contains only a small fraction of the Milky Way's stellar mass, but provides crucial insights into the galaxy's formation. Many halo stars are thought to have originated in smaller galaxies that were torn apart and absorbed by the Milky Way, a process called galactic cannibalism. Chemical tagging and kinematic studies have identified streams of stars with common origins, tracing the remnants of these ancient merger events. Dark matter dominates the mass budget of the Milky Way. While stars, gas, and dust account for roughly 10% of the total mass within the galaxy's virial radius, dark matter makes up the rest. The dark matter halo extends far beyond the visible galaxy, providing the gravitational scaffolding that holds the system together. Rotation curves, measurements of how fast stars and gas orbit at different distances from the center, remain flat or even rise at large radii, indicating the presence of substantial unseen mass. Without dark matter, the galaxy's outer regions would rotate too slowly to match observations. The Milky Way's evolution has been reconstructed through a combination of stellar archaeology, computer simulations, and observations of analogous galaxies. The current picture suggests that the galaxy formed about 13 billion years ago through the collapse of a primordial gas cloud. Early generations of stars formed in the halo and bulge, enriching the gas with heavy elements through supernova explosions. Over time, the gas settled into a rotating disk where subsequent star formation occurred. Mergers with satellite galaxies, particularly the Gaia-Enceladus merger about 10 billion years ago, disrupted the disk and contributed stars to the halo and thick disk. More recently, the Milky Way has been relatively quiescent, with star formation proceeding steadily in the thin disk and only minor mergers with dwarf galaxies. This narrative has been supported by data from missions like the European Space Agency's Gaia satellite, which has measured precise positions, distances, and motions for over 1 billion stars. Gaia's data revealed substructures in the stellar halo, phase space wrinkles, and streams that pointed to past merger events. Chemical abundance surveys, such as those conducted by the Apogee and Gala projects, map the distribution of elements across the galaxy, tracing the history of star formation and nucleosynthesis. The central supermassive black hole, Sagittarius A, has been observed through radio and infrared astronomy. Its mass, approximately 4 million times that of the Sun, has been determined through tracking the orbits of stars that pass very close to it. The black hole is relatively quiescent compared to active galactic nuclei in other galaxies, accreting material only sporadically and producing modest radiation. This quiescence is consistent with a galaxy in a mature, stable phase, rather than one undergoing violent activity. Star formation in the Milky Way proceeds at a rate of roughly 1 to 2 solar masses per year, concentrated in the spiral arms where gas is compressed by density waves. Giant molecular clouds, the birthplaces of stars, are distributed throughout the disk, and their collapse triggers the formation of star clusters. These clusters eventually disperse, spreading their stars throughout the disk. The Sun itself likely formed in such a cluster about 4.6 billion years ago, though the cluster has long since dissolved. The chemical evolution of the galaxy follows a predictable pattern. Early stars formed from nearly pristine gas with very low metallicities. As these stars aged and exploded as supernovae, they enriched the interstellar medium with carbon, oxygen, iron, and other elements. Later generations of stars, including the Sun, formed from this enriched gas, resulting in higher metallicities. The metallicity gradient, the decrease in heavy element abundance from the inner to outer galaxy, reflects this inside-out formation history, with the inner regions forming stars earlier and more intensively. Gas flows play a critical role in sustaining star formation. The Milky Way accretes gas from the intergalactic medium, replenishing what is consumed by star formation or expelled by supernova-driven winds. This accretion is not uniform, but occurs through streams and clouds that fall onto the disk from the halo. Some of this gas may originate from the circumgalactic medium, a diffuse reservoir of hot, ionized gas extending hundreds of thousands of light-years around the galaxy. The balance between gas inflow, star formation, and outflow determines the galaxy's evolution over cosmic time. Magnetic fields thread the galaxy, affecting the dynamics of gas and the propagation of cosmic rays. Observations of polarized light and radio emission reveal a large-scale magnetic field aligned with the spiral arms, as well as smaller-scale turbulent fields. These fields influence star formation by providing support against gravitational collapse in molecular clouds and by channeling the flow of ionized gas. The picture that emerged by the early 2020s was one of a mature, well-understood galaxy. The Milky Way's structure had been mapped in detail. Its history had been reconstructed through multiple independent lines of evidence. Its future evolution, including an eventual merger with the Andromeda Galaxy in about 4 billion years, could be predicted with reasonable confidence. Models of galaxy formation and evolution, tested against observations of the Milky Way and other galaxies, appeared robust. There were open questions, certainly, about the nature of dark matter, the details of early mergers, and the mechanisms driving gas accretion. But the broad outlines seemed secure. This confidence was about to be tested when the James Webb Space Telescope, with its unprecedented infrared sensitivity and resolution, began systematic observations of specific regions of the Milky Way in late 2023. It was expected to refine existing knowledge, to fill in gaps, and to provide exquisite detail on star-forming regions, stellar populations, and the structure of molecular clouds. What it found instead was a set of observations that did not fit comfortably within the established framework. Features appeared in the data that suggested the galaxy's central regions had experienced recent, violent activity. Stellar populations showed unexpected chemical patterns. Structures emerged that had no clear explanation within standard models. The galaxy we thought we knew began to look unfamiliar. These findings were not announced in a single dramatic revelation. They accumulated over months as different research teams analyzed Webb's observations of the galactic bulge, the central molecular zone, and specific stellar populations. Each team initially assumed their results were anomalous, perhaps due to instrumental effects or peculiarities of their specific targets. But as the data accumulated and cross-checks were performed, a pattern emerged. The Milky Way's center had properties that were inconsistent with the idea of a galaxy in a quiescent, mature state. Something had happened there, something recent on astronomical timescales, that the standard model did not predict. And that realization forced a fundamental reassessment of what kind of galaxy we actually inhabit. The James Webb Space Telescope's observations of the Milky Way's central regions leveraged its unique capabilities in ways that transformed what could be seen. The galactic center, located approximately 26,000 light-years from Earth in the direction of the constellation Sagittarius, is one of the most complex and obscured regions in the sky. Vast clouds of dust block optical light, rendering the center invisible to telescopes like Hubble. Radio and X-ray observations penetrate the dust, but reveal only specific components. Radio waves trace ionized gas and magnetic fields, while X-rays highlight hot plasma and energetic processes. Infrared light, which Webb specializes in, passes through dust, while also revealing the thermal emission from cool objects and the light from stars reddened by intervening material. This combination makes infrared observations essential for understanding the galactic center's structure and activity. Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, observed multiple fields within the central few hundred light-years of the galaxy between November 2023 and May 2024. The targets included the central molecular zone, a concentration of dense gas surrounding the supermassive black hole Sagittarius A, regions of active star formation, and portions of the nuclear stellar disk, the dense collection of stars orbiting within the innermost few hundred light-years. The observations were designed to map stellar populations, characterize dust temperatures and distributions, and identify sites of recent or ongoing star formation. The first images returned from NIRCam revealed extraordinary detail. Individual stars, previously blurred together in ground-based observations, stood out clearly. The stellar density in these images was staggering, with thousands of stars visible in fields spanning only a few arc minutes. The colors of the stars, measured by observing them in multiple infrared filters, provided information about their temperatures, ages, and reddening by dust. What immediately struck researchers was the prevalence of young, massive stars, in regions where they were not expected to be abundant. The nuclear stellar disk, a flattened structure of stars orbiting the galactic center, had long been known to contain both old and young stellar populations. The old stars, red giants and other evolved types, were thought to dominate the mass, while young stars formed sporadically in the dense gas of the central molecular zone. However, Webb's images showed that young stars were far more numerous and more widely distributed than previous surveys had indicated. Massive O and B stars, which live only a few million years, appeared scattered throughout the nuclear disk, not just concentrated in known star-forming regions. This was unexpected. Massive stars are rare and short-lived. Their presence indicates recent star formation within the last few million years. The wide distribution of these stars suggested that star formation in the galactic center had been more extensive and more recent than models predicted. Previous infrared surveys, conducted with telescopes like Spitzer and ground-based adaptive optics systems, had identified young stellar clusters, but Webb's superior resolution revealed that many stars previously classified as part of older populations were actually young and massive. Spectroscopic observations using NIRSpec allowed researchers to measure the star's chemical compositions and radial velocities. The spectra showed absorption and emission lines characteristic of hot, luminous stars. But they also showed something unusual. Many of the young stars had chemical abundances that were inconsistent with formation from the gas currently present in the central molecular zone. Specifically, they were enriched in certain heavy elements, such as nitrogen and carbon, beyond what would be expected from standard stellar evolution and nucleosynthesis models. This chemical peculiarity hinted that the gas from which these stars formed had been processed through previous generations of stars more extensively than expected, or that mixing processes had brought material from different regions of the galaxy into the center. Either scenario implied a more dynamic and complex history for the galactic center than the standard picture of gradual evolution. MIRI observations probing longer infrared wavelengths revealed the structure of the dust and the thermal emission from cool material. The central molecular zone, which contains millions of solar masses of molecular gas, appeared as a glowing, filamentary network in MIRI's images. The filaments, threads of dense gas and dust, traced the influence of magnetic fields, turbulence, and gravitational forces. Their temperatures, inferred from the brightness at different wavelengths, ranged from 20 to several hundred Kelvin, with the warmest regions coinciding with sites of active star formation or proximity to hot stars. But MIRI also detected emission that did not correspond to known sources. Diffuse infrared glow, spread across large areas, suggested the presence of warm dust not associated with star-forming regions or individual stars. This dust, with temperatures around 100 to 200 Kelvin, was too warm to be in equilibrium with the ambient radiation field of the galaxy. Something had to be heating it. The distribution of this warm dust was asymmetric, brighter on one side of the galactic center than the other, and showed filamentary structures extending outward from the central region. One hypothesis was that the dust was being heated by a recent energetic event, such as a burst of star formation or an outburst from Sagittarius A. The supermassive black hole, though currently quiescent, is known to have been more active in the past. Observations of gas clouds near the black hole have shown that they are being illuminated by light echoes, reflections of radiation emitted by the black hole hundreds or thousands of years ago. If the black hole experienced a major outburst in the recent past, it could have heated dust across the central region, and that dust might still be radiating the absorbed energy. Another possibility involved supernova-driven shocks. If multiple supernovae exploded in close succession within the galactic center, the combined energy could shock heat gas and dust across large volumes. Supernovae from the young, massive stars detected by NIRCam could contribute to this heating, but the timescales were tight. The stars had to have formed, evolved, and exploded within the last few million years, and their remnants had to still be heating the surrounding material. This required a burst of star formation that was more intense and more synchronized than expected. The asymmetry in the warm dust distribution suggested directional effects. If an outburst from Sagittarius A arm was responsible, the asymmetry could reflect variations in the density of surrounding material, with denser regions absorbing more energy and remaining warm longer. If supernova shocks were responsible, the asymmetry could indicate that the young stars were not uniformly distributed, but concentrated in specific regions, creating localized heating. Webb also observed specific star-forming regions within the central molecular zone, such as Sagittarius B2 and Sagittarius C, among the most massive and dense molecular clouds in the galaxy. These regions are factories for high-mass stars, and Webb's observations provided unprecedented views of the embedded protostars and their surrounding environments. NIRCam images revealed deeply embedded sources, young stars still enshrouded in their natal cocoons of gas and dust, invisible at shorter wavelengths. MIRI detected the warm dust envelopes around these protostars and the outflows they drive, jets and winds that clear material from their vicinity. In Sagittarius B2, Webb identified dozens of new protostellar candidates, increasing the known population significantly. The spatial clustering of these sources suggested that star formation was proceeding in a hierarchical manner, with smaller clumps forming within larger clouds. The masses of the protostars, estimated from their infrared luminosities and surrounding dust masses, ranged from a few solar masses to over 20 solar masses. The most massive sources were beginning to ionize their surroundings, creating compact regions of ionized hydrogen detectable through their infrared emission lines. Sagittarius C, located closer to the supermassive black hole, showed even more extreme conditions. The cloud is being compressed by the strong tidal forces near the galactic center, and the resulting high densities trigger rapid star formation. Webb's images revealed a dense cluster of young stars, many still embedded in dust, surrounded by filaments of shocked gas. The velocities of the gas, measured through Doppler shifts of spectral lines, indicated turbulent motions exceeding 20 kilometers per second, much higher than typical for molecular clouds. This turbulence, driven by stellar winds and supernova shocks, stirred the cloud and influenced where new stars could form. One of the most striking findings was the detection of organic molecules in the gas surrounding young stars. NIRSpec's high-resolution spectra revealed absorption and emission features from polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules that are common in the interstellar medium. PAHs are thought to form in the atmospheres of dying stars and are destroyed by high-energy radiation, so their presence indicates regions where star formation is recent, but not so intense that the molecules have been photodissociated. The abundance and distribution of PAHs in the galactic center provided clues about the chemical evolution of the region and the balance between molecule formation and destruction. Another unexpected observation involved the kinematics of gas near the black hole. Webb detected high-velocity gas clouds, moving at hundreds of kilometers per second in orbits that brought them very close to Sagittarius A. These clouds were not new discoveries. Some had been tracked for years using other telescopes. But Webb's infrared observations revealed that the clouds were not uniform in composition. They showed variations in dust content, temperature, and molecular abundances across their structures. This suggested that the clouds were being tidally stretched and heated as they approached the black hole, with different parts of the clouds experiencing different conditions. The combination of observations from NIRCam, MIRI, and NIRSpec painted a picture of the galactic center that was far more active and complex than anticipated. Young stars were abundant and widely distributed. Dust was warm and asymmetrically arranged. Star formation was proceeding rapidly in massive clouds. Gas near the black hole was dynamically disturbed. Organic molecules persisted despite harsh radiation. Each observation, taken individually, could be accommodated within existing frameworks. But collectively, they suggested that the galactic center was not in a steady state, but was responding to recent or ongoing perturbations. The question was what those perturbations were and what they implied about the Milky Way's recent history. Star formation in the Milky Way's central regions has long been recognized as occurring, but it was thought to proceed at modest rates, limited by the extreme environment. The strong tidal forces near the supermassive black hole, the intense radiation field, and the turbulent magnetized gas all create conditions that inhibit the collapse of gas into stars. While star formation does occur, it was believed to be sporadic and inefficient compared to the disk of the galaxy, where most of the Milky Way's new stars are born. What Webb's observations revealed was evidence for a recent burst of star formation in the galactic center, an episode of intense stellar birth that produced a significant population of massive young stars within the last few million years. This starburst, if that is the appropriate term, was not supposed to happen according to models of galactic center evolution. The evidence came from multiple sources. The distribution and ages of young stars detected by NARCam indicated that a large number of massive stars formed within a relatively short time window, roughly 2 to 6 million years ago. Age dating young stellar populations is challenging, but estimates can be made from the presence of specific types of stars and the properties of stellar clusters. The most massive O-type stars, which live only a few million years, were present in abundance. B-type stars, slightly less massive and longer lived, were even more common. The ratio of O to B stars suggested an age for the population consistent with recent formation. Stellar clusters provided additional constraints. Webb resolved several young clusters in the nuclear stellar disk that had previously been detected as diffuse sources. High-resolution imaging revealed that these clusters contained hundreds to thousands of stars, with the most massive members dominating the infrared luminosity. By comparing the observed stellar populations to theoretical models of cluster evolution, researchers could estimate the clusters' ages and initial masses. The results consistently pointed to formation times between 2 and 5 million years ago, a narrow window on galactic timescales. The spatial distribution of these young stars and clusters was not random. They appeared concentrated in a ring-like structure, roughly 100 to 200 light-years in radius, centered on the galactic nucleus. This ring coincided with regions of dense molecular gas and active star formation observed in previous surveys. However, the number of young stars Webb detected was far higher than expected based on the current star formation rate, inferred from other indicators, such as infrared luminosity and radio continuum emission. This discrepancy suggested that the star formation rate had been significantly higher in the recent past than it is currently. In other words, the galactic center had experienced a starburst, a period of enhanced star formation that has since declined. Starbursts are common in certain types of galaxies, particularly those undergoing mergers or experiencing strong inflows of gas. But the Milky Way is not undergoing a major merger, and its overall star formation rate is relatively steady. A localized starburst in the galactic center was unexpected. The trigger for such a starburst is a critical question. Star formation requires dense gas, and the central molecular zone contains abundant gas. But the gas must be able to collapse under gravity, overcoming turbulence, magnetic support, and tidal forces. Several mechanisms could potentially trigger a burst of star formation. One is a gravitational instability in the gas disk, where perturbations grow and fragment the disk into dense clumps that collapse to form stars. Another is compression by shock waves, which could be driven by supernova explosions, stellar winds, or dynamical interactions. A third possibility involves the inflow of gas from the larger galaxy. If a large amount of gas was funneled into the galactic center over a short period, the increased density could trigger widespread star formation. One is a gravitational instability in the gas disk, where perturbations grow and fragment the disk into dense clumps that collapse to form stars. Another is compression by shock waves, which could be driven by supernova explosions, stellar winds, or dynamical interactions. A third possibility involves the inflow of gas from the larger galaxy. If a large amount of gas was funneled into the galactic center over a short period, the increased density could trigger widespread star formation. The bar structure of the Milky Way is known to drive gas inflows toward the center, but these inflows are typically gradual. A sudden, massive inflow would require an exceptional event, such as the disruption of a gas-rich satellite galaxy or a perturbation from a passing dwarf galaxy. Numerical simulations of gas dynamics in the galactic center have explored these scenarios. Models show that gas orbiting in the central molecular zone can become unstable if its mass exceeds a critical threshold. The resulting fragmentation can produce a burst of star formation that lasts a few million years, before feedback from the newly formed stars disrupts the remaining gas and halts further collapse. This process can repeat episodically, with quiescent periods between bursts lasting tens of millions of years. The young stars themselves provide clues about the conditions of their formation. Spectroscopic observations revealed that many of the massive stars are in binary or multiple systems, orbiting each other at close separations. The binary fraction among massive stars in the galactic center appears higher than in the disk, suggesting that the dense, turbulent environment favored the formation of multiple star systems. This has implications for the evolution of the stellar population, as interactions between binary stars can lead to mass transfer, mergers, and the production of exotic objects like X-ray binaries. Another clue comes from the chemical compositions of the young stars. As mentioned earlier, some stars show anomalous abundances of certain elements. This could result from the gas being pre-enriched by previous generations of stars, or from mixing processes that brought chemically distinct gas into the star-forming region. If the starburst was triggered by an inflow of gas from the disk or halo, that gas might carry a different chemical signature than the gas already present in the galactic center. The starburst also had consequences for the surrounding environment. The formation of thousands of massive stars within a small volume would produce intense radiation fields, strong stellar winds, and eventually, a large number of supernova explosions. These feedback processes inject energy and momentum into the interstellar medium, creating bubbles of hot gas, shock waves, and outflows. Webb's observations showed evidence for all of these effects. MIRI detected extended regions of warm, ionized gas surrounding the young stellar clusters. The gas was heated to temperatures of tens of thousands of Kelvin by ultraviolet radiation from the massive stars. Spectroscopic observations revealed emission lines from ionized hydrogen, helium, and heavier elements, characteristic of regions photoionized by hot stars. The size and brightness of these regions indicated that the radiation from the stars was sufficient to ionize gas across volumes spanning tens of light years. Stellar winds from massive stars also contributed. O-type stars have powerful winds that carry away significant fractions of their mass over their lifetimes, enriching the surrounding medium with processed material. Collectively, the winds from hundreds or thousands of such stars create a superwind that can drive gas out of the star-forming region and into the larger galactic center environment. Webb detected high-velocity gas in outflows, moving at speeds exceeding 100 kilometers per second, consistent with wind-driven acceleration. Supernova explosions, the deaths of the most massive stars, represent the ultimate form of feedback. Given the age of the young stellar population, some of the most massive stars should have already exploded as supernovae. Each explosion releases energy equivalent to the sun's entire lifetime output in a matter of seconds, creating a shockwave that expands into the surroundings. The cumulative effect of multiple supernovae can create superbubbles, cavities of hot, low-density gas surrounded by shells of swept-up material. Evidence for superbubbles appeared in Webb's MIRI images as regions of diffuse, warm infrared emission with sharp boundaries. These structures, spanning tens to hundreds of light years, were interpreted as the walls of expanding bubbles, where shock-heated gas and dust radiated away energy. The temperatures and expansion velocities inferred from the observations were consistent with supernova-driven shocks, though other sources of energy, such as winds or radiation pressure, might also contribute. The starburst raised questions about the future evolution of the galactic center. If star formation proceeds in episodic bursts, the current population of young stars represents only the latest episode. Previous bursts would have left behind populations of older stars, now mixed into the broader stellar distribution. Detecting these older populations and determining their ages would provide a chronology of star formation in the galactic center, revealing whether bursts occur regularly or sporadically. The starburst also had implications for the supermassive black hole. The feedback from massive stars, particularly supernova explosions, can drive gas flows that either feed or starve the black hole. Outflows might expel gas that would otherwise accrete, reducing the black hole's growth rate. Conversely, the compression and heating of gas by shocks might funnel material inward, enhancing accretion. Understanding this interplay between stellar feedback and black hole growth is crucial for modeling the coevolution of galaxies and their central black holes. What the starburst revealed was that the Milky Way's galactic center was not a static environment, but one that had recently undergone a dramatic transformation. The formation of a large population of massive stars in a short time represented an injection of energy, mass, and momentum that reshaped the region's structure and dynamics. The standard model of gradual, steady evolution did not predict this. Something had disturbed the equilibrium, triggering the burst. Identifying that trigger and understanding its consequences was essential for comprehending the galaxy's recent history and future trajectory. Among the most puzzling findings from Webb's observations of the galactic center were the chemical compositions of stars, both young and old, that did not match theoretical predictions. Stellar spectroscopy, the analysis of light dispersed into its component wavelengths, allows astronomers to determine the abundances of elements in a star's atmosphere. These abundances reflect the composition of the gas from which the star formed, modified by nuclear reactions in the star's interior, and, in some cases, by mass transfer in binary systems or pollution from companion stars. The chemical composition of stellar populations provides a fossil record of the galaxy's history, tracing the buildup of heavy elements over time and revealing the mixing and transport of gas across the galaxy. What Webb found in the galactic center were stars whose chemical fingerprints did not fit the established narrative of Milky Way chemical evolution. The standard model of galactic chemical evolution posits that the Milky Way formed from metal-poor gas, with the first stars containing almost no elements heavier than hydrogen and helium. These stars, through their lives and deaths, produced carbon, oxygen, nitrogen, iron, and other elements, which were expelled into the interstellar medium via stellar winds and supernova explosions. Subsequent generations of stars formed from this enriched gas, inheriting higher metallicities. Over billions of years, the average metallicity of the galaxy increased, with the enrichment proceeding faster in the inner regions, where star formation was more intense. This inside-out chemical evolution creates a metallicity gradient, with stars in the galactic bulge, an inner disk being more metal-rich than those in the outer disk and halo. The gradient has been measured in detail through surveys like apogee, which uses near-infrared spectroscopy to observe hundreds of thousands of stars across the galaxy. The observed gradient matches models reasonably well, supporting the overall picture. However, Webb's spectroscopic observations of stars in the nuclear stellar disk revealed significant deviations from this pattern. NARSPEC obtained high-resolution spectra of dozens of stars, including young massive stars, red giants, and intermediate mass stars. The spectra showed absorption lines from various elements, and measuring the depths and widths of these lines allowed researchers to determine elemental abundances. The young massive stars, those formed in the recent starburst, showed anomalies in their nitrogen, carbon, and oxygen abundances. Specifically, they were enriched in nitrogen relative to oxygen and carbon compared to expectations. Nitrogen is produced in the cores of massive stars through the CNO cycle, a set of nuclear reactions that convert hydrogen to helium while cycling carbon, nitrogen, and oxygen. In standard stellar evolution, nitrogen enrichment occurs in the later stages of a star's life and is expelled when the star becomes a red giant or explodes as a supernova. For young stars to show high nitrogen abundances, they must have formed from gas that had already been processed through previous stellar generations. This could occur if the gas from which the starburst formed had been enriched by an earlier population of massive stars that evolved, enriched the medium, and then allowed new stars to form from the processed material. But the timescales were problematic. The young stars were only a few million years old. For their formation gas to be nitrogen-enriched, the previous generation would have had to form, evolve, and die within a few tens of millions of years before the starburst. This implied a very recent cycle of star formation and enrichment, a process that was not evident in other observations. Alternatively, the nitrogen enrichment could result from mixing processes that brought nitrogen-rich gas from elsewhere in the galaxy into the galactic center. The bar can drive gas inflows, and if gas from the inner disk, which might have different chemical properties, was funneled into the center, it could create localized anomalies. However, models of bar-driven inflows do not predict the specific pattern of enrichment observed. Another hypothesis involved Wolf-Rayet stars, a class of massive stars that have lost their outer hydrogen envelopes and are fusing helium in their cores. Wolf-Rayet stars expel nitrogen-rich material through intense stellar winds. If a population of Wolf-Rayet stars existed in the galactic center just before the starburst, their winds could have enriched the surrounding gas with nitrogen. The young stars would then inherit this signature. Webb did detect several Wolf-Rayet candidates in the nuclear stellar disk, identified by their characteristic emission lines, supporting this scenario. The old stars in the nuclear stellar disk also showed chemical peculiarities. Red giants, which are evolved stars in later stages of their lives, were observed with NIR spec to determine their iron, magnesium, and alpha element abundances. Alpha elements, such as oxygen, magnesium, and silicon, are produced in massive stars and expelled in core collapse supernovae. Iron is produced both in core collapse supernovae and in type Ia supernovae, which occur when white dwarfs in binary systems explode. The ratio of alpha elements to iron, often denoted Fe, is a diagnostic of star formation history. Regions with rapid star formation produce high Fe ratios because massive stars, which explode quickly as core collapse supernovae, dominate the enrichment. Regions with slower star formation have lower Fe ratios because type Ia supernovae, which occur on longer timescales, contribute more iron. The Fe ratio thus traces the speed of chemical enrichment. Webb's observations revealed that many red giants in the nuclear stellar disk had Fe ratios that were lower than expected for their metallicities. This suggested that these stars formed from gas that had been enriched over a long period, with significant contributions from type Ia supernovae. But this was inconsistent with the idea that the galactic bulge, which includes the nuclear stellar disk, formed rapidly in the early universe. Rapid formation should produce high Fe ratios, not low ones. One interpretation was that the nuclear stellar disk was not a homogeneous population, but contained stars from multiple formation episodes and locations. Some stars might have formed in situ, in the galactic center, while others migrated there from the inner disk or were captured from merging satellite galaxies. One interpretation was that the nuclear stellar disk was not a homogeneous population, but contained stars from multiple formation episodes and locations. Some stars might have formed in situ, in the galactic center, while others migrated there from the inner disk or were captured from merging satellite galaxies. This mixing would create a chemically heterogeneous population with a range of AAFE ratios and metallicities that did not follow a simple pattern. Chemical tagging, the practice of grouping stars by their detailed chemical compositions to identify common origins, revealed subpopulations within the nuclear stellar disk. Some groups of stars shared similar patterns of abundances across many elements, suggesting they formed together or from the same gas reservoir. Other stars appeared chemically distinct, with no clear matches to known stellar populations in the disk or halo. These orphan stars might represent remnants of small galaxies or star clusters that were disrupted and absorbed by the Milky Way. Another striking finding involved europium and other rare Earth elements. These elements are produced primarily in neutron star mergers, the violent collisions of compact remnants of massive stars. The presence and abundance of europium in stars traces the frequency of neutron star mergers in the environment where the stars formed. Webb detected europium absorption lines in several red giants, allowing abundance measurements that were more precise than previous studies. The europium abundances were higher than expected for stars of their age and metallicity. This suggested that the galactic center had experienced a higher rate of neutron star mergers than the rest of the galaxy. Neutron star mergers are rare events, typically occurring long after the stars that produce the neutron stars have formed and evolved. A high merger rate could result from a large population of massive binary stars, many of which would evolve into binary neutron star systems. Over time, gravitational wave emission would cause these systems to spiral together and merge. The link between the recent starburst and the high europium abundances was unclear. If the starburst produced many massive binary stars, those systems would not merge for millions to billions of years, far longer than the age of the starburst. The high europium must therefore reflect enrichment from earlier stellar populations. This implied that the galactic center had been a site of intense star formation, not just recently, but also in the more distant past, producing multiple generations of massive stars and eventually neutron star mergers. The chemical anomalies extended to isotopic ratios, though these are much harder to measure. Certain isotopes of carbon, nitrogen, and oxygen can be distinguished through high-resolution spectroscopy by analyzing molecular features in cool stars. These isotopic ratios are sensitive to specific nuclear processes and can reveal details about the stellar sources of enrichment. Webb's NEOSPEC, with its high spectral resolution, detected molecular absorption from carbon monoxide and other molecules in the atmospheres of cool giants, allowing preliminary isotopic measurements. The carbon-12 to carbon-13 ratio, a commonly measured isotopic diagnostic, showed variations among stars that could not be explained by standard stellar evolution alone. Some stars had unusually high carbon-13, which is produced in asymptotic giant branch stars and through certain nuclear burning processes. The distribution of isotopic ratios hinted at complex mixing histories, with gas from different sources blending in the galactic center. The implications of these chemical anomalies were profound. They indicated that the galactic center's enrichment history was not a simple, monotonic process, but involved multiple episodes of star formation, feedback, and mixing. The chemical signatures recorded in stellar atmospheres told a story of a dynamic environment where gas was continuously being processed, expelled, and accreted. The standard models of galactic chemical evolution, which treat regions like the bulge as relatively isolated and uniformly evolving, were inadequate for the galactic center. Moreover, the anomalies suggested that the galactic center had been influenced by processes not typically included in models. These might include gas inflows from the disk driven by the bar, accretion of gas-rich satellites, or turbulent mixing that transported material across large distances within the bulge. Each of these processes would leave distinct chemical fingerprints, but disentangling them required more extensive observations and sophisticated modeling. What the chemical anomalies revealed was that the stellar populations in the Milky Way's center carried a record of the galaxy's history that was richer and more complex than anticipated. The abundances of elements were not simply consistent with slow, steady evolution, but pointed to episodes of rapid change, intense star formation, and significant mixing. Understanding this chemical complexity was essential for reconstructing the galactic center's history and for placing it within the broader context of the Milky Way's evolution. The stars were messengers from the past, and their chemical compositions were the messages. Webb had provided the means to read those messages with unprecedented clarity, and what they revealed did not match the expected narrative. The central molecular zone, the concentration of dense gas within the innermost few hundred light-years of the Milky Way, has long been recognized as one of the galaxy's most extreme environments. It contains roughly 10% of all the molecular gas in the galaxy, compressed into a tiny fraction of the galactic volume. Gas densities reach values orders of magnitude higher than in typical molecular clouds in the disk. Temperatures are elevated due to the intense radiation field from the millions of stars in the bulge and the proximity to the supermassive black hole. Tidal forces from the galactic gravitational potential shear and stretch the gas. Magnetic fields, amplified by compression and turbulence, thread the clouds. Despite these harsh conditions, or perhaps because of them, the central molecular zone is a region of active star formation and complex chemistry. What Webb's observations revealed was that this activity was far more widespread and energetic than previously recognized, with signatures of processes that challenged existing models of how molecular clouds behave and evolve. MIRI's imaging of the central molecular zone captured the thermal emission from dust grains embedded in the gas. Dust temperatures varied across the region, with the warmest dust approaching 300 to 400 Kelvin, located near sites of active star formation where young stars heat their surroundings. Cooler dust, at temperatures of 20 to 50 Kelvin, filled the spaces between star-forming regions, representing the bulk of the molecular gas that had not yet collapsed to form stars. The distribution of dust temperatures revealed the structure of heating sources and the efficiency with which energy propagated through the gas. What was unexpected was the presence of warm dust in regions where no obvious heating sources existed. Large areas of the central molecular zone showed dust temperatures of 100 to 200 Kelvin, intermediate between the cold ambient gas and the hot star-forming regions. This warm component represented a significant fraction of the total dust mass, implying that substantial amounts of energy were being deposited into the gas across the entire central molecular zone, not just in localized star-forming cores. The source of this widespread heating was not immediately clear. Cosmic rays, high-energy particles that pervade the galaxy, can heat gas through ionization and collisional excitation. The central molecular zone is thought to have an elevated cosmic ray density due to the high rate of supernova explosions and the proximity to the galactic center's accelerating environments. Cosmic ray heating could contribute to the observed temperatures, but models suggested it was insufficient to account for the full extent of the warm dust. Mechanical heating from turbulence offered another mechanism. The gas in the central molecular zone is highly turbulent, with velocity dispersions exceeding 20 kilometers per second, much higher than in disk molecular clouds. This turbulence, driven by stellar winds, supernova shocks, and gravitational instabilities, dissipates energy as heat. When gas clouds collide, or when shocks propagate through the medium, kinetic energy converts to thermal energy, raising temperatures. Webb's observations of velocity fields, obtained through NIR spectroscopy of emission lines, revealed complex chaotic motions consistent with turbulent dissipation. Another possibility involved magnetic reconnection, a process where magnetic field lines break and reconfigure, releasing energy. The central molecular zone has strong, dynamically important magnetic fields. Where field lines converge or become tangled, reconnection events can occur, heating gas and accelerating particles. Observational signatures of reconnection are difficult to detect directly, but indirect evidence, such as localized heating or non-thermal emission, might appear in Webb's data. Researchers were analyzing the MIRI images for hotspots or filaments that could indicate reconnection sites. The chemistry of the central molecular zone also showed unexpected features. NIR-SPEC's spectroscopic observations detected emission and absorption from a wide range of molecules, including carbon monoxide, water, methanol, ammonia, and more complex organic species. The abundances and excitation states of these molecules provided information about the physical conditions of the gas, including density, temperature, and radiation field strength. One surprising result was the detection of complex organic molecules in regions far from active star formation. Molecules like methanol and formaldehyde typically form on the surfaces of dust grains in cold, dense gas and are released into the gas phase when the grains are heated or disrupted. Their presence in widespread, moderately warm gas suggested that either the gas had been heated recently, vaporizing molecules from grains, or that chemical pathways in the central molecular zone differed from those in the disk. The water abundance was another anomaly. Water is one of the most important molecules in astrochemistry, and its abundance traces the availability of oxygen and the history of gas processing. Webb detected strong water absorption and emission features in many locations throughout the central molecular zone. The inferred water abundances were higher than models predicted for gas at the observed temperatures and densities. This could indicate that water ice on dust grains was being sublimated more efficiently than expected, possibly due to enhanced heating or shock processing. Isotopic ratios in molecules also showed variations. The ratio of deuterium to hydrogen, measurable through observations of deuterated molecules like deuterated water or deuterated molecular hydrogen, varied across the central molecular zone. Deuterium fractionation, the preferential incorporation of deuterium into molecules, occurs in cold, dense gas and is temperature sensitive. The observed variations suggested that different regions had different thermal histories, or that mixing was bringing gas from disparate environments into contact. Another striking observation involved ionized gas. While much of the central molecular zone is molecular, regions of ionized hydrogen exist, where ultraviolet radiation from hot stars strips electrons from atoms. Webb detected infrared emission lines from ionized gas, including fine structure lines from ionized carbon, nitrogen, and oxygen. These lines are bright in the mid-infrared and serve as diagnostics of ionization conditions and gas density. The spatial distribution of ionized gas was complex. It appeared not only around known clusters of hot stars, but also in filaments and bubbles extending far from obvious ionization sources. This suggested that ionizing radiation was escaping from star-forming regions more efficiently than expected, perhaps through low-density channels or cavities cleared by winds and explosions. Alternatively, shocks could be ionizing the gas through collisional processes, independent of stellar radiation. The relationship between the molecular gas and star formation was also non-standard. In the disk of the Milky Way, the star formation rate correlates with the amount of dense molecular gas, according to well-established empirical relations, such as the Kennicutt-Schmidt law. However, in the central molecular zone, the star formation rate appeared lower than these relations would predict, given the large mass of dense gas. This star formation deficit has been recognized for years and is attributed to the extreme conditions, turbulence, tidal forces, and magnetic fields that inhibit gravitational collapse. Webb's observations provided new insights into this inefficiency. By mapping the distribution of dense gas at high resolution and identifying star-forming cores, researchers could assess where star formation was occurring and where it was not. The results showed that star formation was highly localized, confined to specific dense clumps within the larger molecular clouds. Most of the gas, even dense gas, was not forming stars. This suggested that additional barriers beyond density were preventing collapse, such as strong magnetic support or disruptive tidal forces. The role of feedback in regulating star formation also became clearer. Webb detected numerous outflows, jets, and winds driven by young stars and supernova remnants. These outflows disrupted surrounding gas, compressing some regions and dispersing others. The net effect was to create a patchy, chaotic distribution of star-forming and quiescent regions. Feedback thus acted as both a trigger and a suppressant of star formation, depending on local conditions. The central molecular zone's activity had implications for the galaxy's overall gas budget and star formation history. If the central molecular zone is a reservoir of gas that is slowly being consumed by star formation and feedback, understanding the balance between gas inflow, star formation, and gas removal is crucial for predicting the galactic center's future. If inflows from the disk replenish the gas, the central molecular zone could sustain star formation indefinitely. If feedback expels gas faster than it is replenished, the star formation rate will decline. What Webb's observations of the central molecular zone revealed was that this environment was not a static gas reservoir, but a dynamic, evolving system where gas was being heated, stirred, chemically processed, and converted into stars at rates and in patterns that did not conform to simple models. The hidden activity, obscured by dust at optical wavelengths but revealed in infrared, indicated that the galactic center was a site of ongoing transformation. Understanding the processes driving this activity was essential for comprehending not just the center itself, but how it influenced the galaxy as a whole. Sagittarius A, the supermassive black hole at the Milky Way's center, is currently in a quiescent state, accreting material at a very low rate and emitting only faint radiation across the electromagnetic spectrum. Observations over the past few decades have established that the black hole has a mass of approximately 4 million solar masses, and that its immediate environment is relatively calm. Gas and stars orbit the black hole, but there are no dramatic accretion disks, jets, or outbursts like those seen in active galactic nuclei in other galaxies. However, evidence has accumulated over the years suggesting that Sagittarius A was more active in the relatively recent past, on timescales of hundreds to thousands of years. What Webb's observations added to this picture was new evidence that the black hole experienced a significant outburst, or series of outbursts, within the last few thousand years, and that the effects of this activity were still detectable in the surrounding gas and dust. The primary evidence came from light echoes, reflections of radiation emitted by the black hole that illuminate gas clouds at various distances. When Sagittarius AI experiences an outburst, it emits intense X-rays and ultraviolet radiation. This radiation travels outward at the speed of light, eventually encountering gas clouds. The radiation ionizes and heats the gas, causing it to glow. Because the light takes time to travel from the black hole to distant clouds, the glow appears delayed relative to the outburst, creating an echo effect. By observing these echoes, astronomers can reconstruct the history of the black hole's activity. Previous observations in X-rays and optical wavelengths have detected light echoes from molecular clouds several hundred light-years from Sagittarius A. These observations suggested that the black hole was much brighter a few hundred years ago, possibly 1 million times brighter than it is today. Webb's infrared observations extended this analysis by detecting thermal emission from dust that had been heated by past radiation from the black hole. MIRI images showed faint, diffuse infrared emission from dust clouds located at various distances from Sagittarius A, ranging from a few light-years to over 100 light-years. The temperatures of these clouds, inferred from their infrared spectra, were higher than would be expected from ambient heating by the galactic radiation field. Moreover, the spatial pattern of the warm dust formed shells and arcs that appeared to be expanding away from the black hole's location. This morphology was consistent with dust being heated by a pulse of radiation that originated from Sagittarius A and expanded outward. The timing of the outburst could be estimated from the geometry. Light from the black hole reaches clouds at different distances at different times. By measuring the distances to the warm dust clouds and comparing them to the speed of light, researchers could calculate when the radiation that heated them was emitted. The results pointed to an outburst that occurred roughly 1,000 to 6,000 years ago, consistent with previous estimates from X-ray light echoes, but providing independent confirmation. The intensity of the outburst could also be inferred from the amount of energy required to heat the dust to the observed temperatures. Models suggested that Sagittarius A must have been between 100,000 and 1 million times more luminous than it is currently. This level of luminosity corresponds to a moderate accretion event, where the black hole consumed a significant amount of material over a relatively short period, perhaps decades to centuries. The material could have come from the disruption of a star, a gas cloud, or the accumulation of smaller amounts of material over time that suddenly became unstable and fell inward. Spectroscopic observations added detail. NIRSpec detected emission lines from ionized gas in some of the clouds illuminated by the light echo. The ionization states indicated exposure to a hard radiation field, consistent with X-rays and extreme ultraviolet photons from an accreting black hole. The velocities of the ionized gas, measured through Doppler shifts, showed that some clouds were moving at hundreds of kilometers per second, possibly driven by radiation pressure or winds from the accretion event. Another line of evidence came from the structure of the gas near the black hole. Webb observed the so-called mini-spiral, a set of ionized gas streams orbiting within a few light-years of Sagittarius A. The mini-spiral has been studied for decades using radio and infrared observations, and its kinematics and morphology have been well characterized. Webb's high-resolution imaging revealed fine structure within the mini-spiral, including clumps, filaments, and gaps that had not been clearly resolved before. Some of these features appeared to be shock-heated, with temperatures and velocities inconsistent with simple orbital motion. One interpretation was that the gas had been disturbed by an outflow or wind from Sagittarius A during a past active phase. Winds from accreting black holes can reach velocities of thousands of kilometers per second and carry substantial momentum. If Sagittarius A drove such a wind during its recent outburst, the mini-spiral gas could have been swept up, compressed, and accelerated, leaving behind the observed shocked features. The presence of molecular gas very close to the black hole also provided clues. Webb detected infrared emission from molecules in gas clouds, orbiting within a few light years of Sagittarius A. The molecules, particularly carbon monoxide and water, are fragile and easily destroyed by ultraviolet radiation and X-rays. Their survival suggested that the radiation field near the black hole was currently weak, allowing molecules to persist. However, the distribution of molecules was patchy, with some regions showing strong molecular emission and others showing none. This patchiness could reflect the recent history of radiation exposure, with molecules surviving in regions shielded from the outburst and being destroyed in regions that were directly exposed.